Hey there, we've made it to chapter 7, our penultimate chapter, because we won't do chapter 8. Okay, so chapter 7 is often really fun. I think this is where people think about chemistry when they're little, because it's how we imagine it's the Lewis dot structures and the geometry and the, things like this that you get to play with. I think that's one of the things that's sad about not having this in class is that you won't be doing this with manipulatives, which is, it's really kind of fun. It's a chance for students to think 3D and do hands-on 3D, just like they were back learning hands-on again when they were little. So anyway, you definitely don't need to go out and buy a molecular model kit for this class by far. If you want to own them, that's great. If you have kids and you own one, they'll play with them. I have 3, my kids steal them. So, but anyway, it's really kind of a fun chapter. Okay, first, electronegativity. All right, electronegativity is the ability of an atom and a molecule to attract shared electrons to itself. On the periodic table, electronegativity generally increases across a period and decreases down a group. The range of electronegativity values is from 4.0 for fluorine, the most electronegative, to 0.7 for cesium and francium, the least electronegative. All right, so this is such a fun chart, I think. It's a topographical map of the periodic table. And if you can't see the whole thing in the video, like if my screen is covering up like the fluorine or something, you do have it in the slides that you have access to. And this is so cool. I first of all, I like topographical maps just in general, but this one really helps you see. So down here we have 0.7 for francium and cesium. And those are the lowest electronegativities, and you can see that down here. And then up here, you have fluorine. And fluorine is the most electronegative atom in the periodic table. And sometimes you have these perfect stair steps. And of course, in the transition elements, things get a little weird, but we've been seeing that all along. So you can really see this amazing trend in electronegativities, from the largest up here to the smallest down here. And again, that electronegativity is how tightly it's pulling on shared electrons. So right now, mostly with electronegativity, we're thinking and talking about covalent bonds. All right, so let's take a look at some options. And it says, let's arrange the following bonds from the most polar to the least polar. Okay, and one kind of nice, easy way to do that is to think about them in terms of their electronegativities. So we see here that nitrogen is 3 and fluorine is 4. And that gives those a difference of 1. And oxygen is 3.5 and fluorine is 4, and that gives them a difference of 0.5. And carbon is 2.5 and fluorine is 4, so that gives them a difference of 1.5. Now they want, and this is very important here, the slide is asking for most to least polar. Okay, so that means the largest difference to the smallest difference. And the largest difference here is carbon to fluorine. And the smallest difference that we have here is oxygen to fluorine. And that leaves our nitrogen fluorine in the middle. Okay, okay. Now let's take a look at our next one. Here we have carbon to fluorine. Okay, so you can see, we remember that carbon to fluorine from the previous line has a difference of 1.5. And now nitrogen to oxygen, this goes from 3 to 3.5. So this gives us a difference of 0.5. Now we have our silicon to fluorine, and silicon is right here, and it's 1.8. to fluorine 4. So that one actually has a difference of 2.1. Wow. Oh, so 2.2. Yeah, having trouble adding tonight. 2.2. Okay. So clearly the most polar one that we have here is silicon to fluorine. And the least polar is nitrogen to oxygen. And the carbon fluorine is in the middle. All right, and now let's go ahead and we'll look at our last one here. Well, look, chlorine to chlorine, the difference is always going to be 0 when they're the same. So we know that the least polar that we have here is the chlorine to chlorine bond. Now we look at boron. Boron is 2. Chlorine is 3. So that gives that one a difference of 1. And sulfur, 2.5 to chlorine. So that one is a difference of 0.5. Okay. So now the most polar one in this list is boron to chlorine, and sulfur to chlorine goes in the middle. And that is how you would rank these from most polar to least polar. So in this one, let's take a look only at these here. Okay. And I'm going to give you a little preview of something that we're going to be doing very soon. And that's called drawing a dipole. So let's look at our most polar. See how we have carbon at 2.5 and fluorine at 4? That means that the fluorine is pulling on those electrons really hard compared to the carbon. Okay, so you could draw this. And that is a dipole. And it says, okay, it's pointing to the fluorine because that's the most electronegative. And you can see this little positive sign on the carbon indicating that it has a delta positive because it's less electronegative. And the same thing, fluorine. So whenever you have fluorine in something, unless it's like diatomic fluorine gas, it's always going to point to fluorine, right? Silicon to fluorine. And then we have boron to chlorine. Okay, well, boron is only 2 and chlorine is 2. So that means that this one is going to go in this direction also. And they won't always go from left to right. That just happens to be how they were drawn in this case. Okay, but what I've done here in red is just a little preview of what's called a dipole, where you draw an arrow that's pointing at the more electronegative atom. I have trouble getting it. There we go. All right, now we're looking at some ionic bonds. Ionic bonds are electrostatic forces of attraction between oppositely charged cations and anions. Okay, so in this picture, we are making sodium chloride. Okay, and so here we have the chlorines and the sodiums. Okay, and you'll never have a single molecule of sodium chloride like this. This doesn't exist, okay? We draw a big X through it. What you have, and I've actually seen these are with lines between them, but I think that gives a poor picture of it. This is a great, it's called a space filling model here, and that one's really good. But the best way that I see this is with dots between the atoms. Okay, so imagine, because they're not actual bonds like we think of them, they're electrostatic forces. And so another way that I have seen these drawn is more like this. Okay, and if you go on to Chem 2, you will find that there's a lot of different ones. There's simple cubics and body-centered cubics, and these just keep going and going. Fluorine, you can see that I'm making these interlocking grids where I'm drawing dots to combine, that, right? Okay, and they're all sort of partially bonded to a whole bunch of stuff. So don't imagine that these electrostatic bonds are these solid bonds between ions like the covalent bonds, okay? So make sure that you imagine them. You can kind of see how I do that all with dotted, like partial bonds. It's a different kind of a bond. Okay. All right, now covalent bonds is a little different. Now remember, in covalent bonds or molecules, we're sharing. And so what this is showing is that potential energy is basically, it's kind of like a neutral state, right? It's neither favored nor unfavored. And you could say that the potential energy of a molecule at 0 is your neutral. So you basically are approaching 0 when you have these here. Now, a molecule or a bond is likely to form at our lowest possible energy level. So you can see here, we have our lowest potential energy as negative 458 kilojoules per mole when you have a bond length of 0.074. Okay, and that's an internuclear distance in nanometers. So nanometers at 0.074 nanometers, wow, that is really small. That is let's see, 1, 2, 3, 4, 5, 6, 7, 8. I'm thinking here, okay, like this. Okay, 7.4 meters. Very small. All right, so now let's take a look. We've got electronegativity and bond difference. Okay, so if we have 0 difference between the two, remember we had that chlorine to chlorine bond, and it has 0 difference between the atoms. That makes something that's purely covalent. Okay, so those pure covalents, the most common ones are your diatomic gases, okay? So hydrogen gas, oxygen gas, nitrogen gas, chlorine gas, fluorine, iodine, bromine, okay? So that's one of the things that you can get. And then there's also a few times where things are very, very close, but not quite close enough. And another one that's pure covalent, they have this electronegativity difference here. I would say between or less than or equal to 0.4, because I would also consider the carbon hydrogen bond to be purely covalent, and it has an electronegativity difference of only 0.4. Okay, now we have these intermediate or polar covalent bonds. Actually, before we do that one, let's look at these ionic bonds here. Less than, greater than 1.8. Now, let me see if I have that on the next slide. Nope. Okay, so there's most of the time you have something that's ionic if it's greater than or equal to 1.8 electronegativity difference. However, there are some exceptions to that. One of the primary exceptions, and yeah, I'm coming to this one in a minute. One of the primary exceptions to that is HF, hydrofluoric acid. Okay, hydrofluoric acid has an electronegativity difference of 1.9, but it is definitely polar covalent, and it is very strongly held together. In fact, it's significantly, even though it looks like it's almost ionic, it's significantly more strongly held together than, say, hydrochloric acid, which has a much smaller electronegativity difference. So hydrofluoric acid would be polar covalent, even though it doesn't fall into here. But most of the time, polar covalence will happen between 0.4 and 1.8. And the way we kind of avoid that is that this is a good guideline for the electronegativity difference. But remember, something is ionic if it begins with a metal. Or the ammonium ion, but we won't be doing a lot of that in here because we'll be looking mostly at binary things right now, especially in the ionic. So remember, ionic begins with a metal, okay? And that's a more important rule than this 1.8, all right? And now you can see here we have hydrochloric acid. And remember that our hydrogen here had a, I'm going to take a peek. There we go. Has an electronegativity. I don't have them memorized. Well, I don't have all of the electronegativities memorized. 2.1 to chlorine at 3. No, it's on the slide. See, I don't read the slides when I'm lecturing. Okay. And that means that we have 0.9. Now, because hydrogen only has an electronegativity of 2.1, it's not pulling as hard on the electrons as chlorine is. And that's why you can draw this dipole, and they've drawn it up here. But when you're going to draw a dipole moment, you would actually draw it straight through the center like this. Okay. And we'll get to dipole moments at multiple times in the chapter. All right, so the first section where we're looking at dipole moments is here where we compare water and carbon dioxide. Okay, so a dipole moment is an overall charge separation. So you can see on these hydrogens that we have what's called a delta positive. Okay, and on the oxygen, we have a delta negative. And we actually have a 2 delta negative because oxygen often forms a -2, even though in this case, they're sharing, there's no charges. What this gives us is a charge separation. And what we can do is we can say, you can almost draw this kind of line like this. And this side of the molecule is positive, and this side of the molecule is negative. And if you can draw kind of that magic line, so to speak, then you can draw a dipole straight through the whole thing, or like this. And you can see the way it's drawn, you've got, these bluish to the red. Now, when you have something like carbon dioxide, though, then things change a little bit because your carbon is right around 2.5 and your oxygen, I'm trying to remember if it's, yeah, it is 3.5. It's 3.5. Okay. And so that means that definitely what you see is the electrons being drawn to the outside. But see how they cancel themselves out? Because the dipoles balance each other out. Like up here, you could draw little dipoles like this. And see how they both kind of point in the same direction? All right, well, in this, the dipoles are going in opposite directions. So there's a dipole moment in water, but there is no dipole. You can't even see that at all. But there is no dipole moment here. There we go. No dipole moment at all in something like carbon dioxide will they balance out. Okay, so this is super fun. We've got our molecular models. Okay, so models are attempts to explain how nature operates on the microscopic level based on experiences in the macroscopic world. They're not exact, and the reason I have that statement in there about models isn't so that you think that any of these drawings here are what a methane molecule actually looks like. You don't have these tiny little things. My kids love the Marvel movies, and you have the quantum realm, and you go down there and everything looks weird. So it's almost like, oh, well, that's interesting. As a scientist, I don't think so, but okay. And you need to think about the same kind of thing here, is it's not going to be exact. However, we have 3 different ways of seeing that. This first one is what's called a space filling model. And if anything, the space filling model is probably the best one out of all of the models because it shows your atomic orbitals meshing into molecular orbitals, and nothing else really shows that overlap of orbitals. What this is doing, this structure in the middle, it's a 3D Lewis dot structure. If you go on to take organic structure, these would specifically be called Kekulé structures. Okay, and what they're doing is they're drawn in such a way where you have this one is up, and then this one, this wedge means that it's coming out of the paper, and the dots means that they're going backwards. And you can sort of see that in here where you can have this one is up and down, and this one is coming towards you, and this one, like this, a lot of times you'll draw them with the graduated ones, is drawing to the back. And you can see the same thing here in a ball and stick physical model, like these are, okay? And again, this one is going up, this one is coming out towards you, and then you have these going back. Okay, So now we have come to the localized electron model. A molecule is composed of atoms that are bound together by sharing electrons. Okay, so there's two different kinds of electrons in a Lewis dot structure or a localized electron model. And here we kind of have a structure that shows water. Okay, so first of all, lone pairs here are the pairs of electrons that are localized on an atom, and those are shown here and here. Those are lone pairs, and these lone pair electrons are stuck on the oxygen. Then you have these lines right here, and these lines are each what's called a bonding pair. And these lines are the electrons, there's two in each line, that happen between the hydrogen and the oxygen. So they're used in bonding rather than localized. Okay, so I love this. It's a lot of you know this is our first go around using OpenStax, and I used to include this every time I taught for another book. This is actually the first book I've taught out of, and I've taught out of quite a few that had this, which I think is just so cool. So what they're doing here is they're showing a variety of atoms, and I think all the ones they are showing, yep, all the ones they are showing, turn on my annotation. All of these that they are showing are in row 3. Okay, and you can see your neon and the 3s1, 3s2, 3s2, 3p1, and all the way down to 3p6 are noble gas. Okay, so here you have 1 electron on sodium and 2 electrons on magnesium and 1, 2, 3 electrons on aluminum. And then what I'm going to do here is I'm going to draw a little line right across like that. And why did I draw that line? Because these are all metals. And we're not really going to talk about them as much because they only form ionic bonds. Well, that's not true. Metals bond to each other with actual bonds, but that's completely different. You won't do that until you get to Chem 2. And we don't want to talk about that at all right now. But these metals, these form cations. Okay, so there's no share. And I'm not going to be drawing little openings for them to share in. Okay, now things are going to be a little bit different though when we come down here. Here we have nonmetals. Okay, and our nonmetals, they can form anions, but we're not going to look at them in terms of anions really in this chapter. We're going to look at them in terms of covalent bonds. Okay, now look, silicon has 1, 2, 3, 4. Phosphorus has 1, 2, 3, 4, 5. Okay, and you'll notice that you don't have any empty spaces here, right? You have at least 1 electron on each side. Okay, and I'm making them blue. You can see where I'm identifying them. Now what I'm going to do is I am going to use lavender, and I'm going to put a dot everywhere that we have a place that could be filled for bonding. Now let's look down here on argon. See how we have 2, 2, 2, 2, 2, 4, 6, 8, 4 sets of 2. Argon has no spots for bonding. So we'll say no bonding sites. Okay. Chlorine has 1 right here. Sulfur has 2 here and here. And everywhere I'm drawing a lavender dot is a place where we could bond. 1, 2, 3. 1, 2, 3, 4. Now it doesn't always work like that. Phosphorus could have more than 3 bonds. Sulfur could have more than 2 bonds. Every now and then you'll see something weird where sulfur will have only 1. And we'll cover that a little bit more in depth when we talk about expanded octets and formal charges. But what this is doing is this is showing you where these are and how I want you to think of them. For example, like let's look at that phosphorus there. Okay, so we have a lone pair here, and then here we have our electrons. Okay, and here's a site for bonding, and here's a site for bonding, and here's a site for bonding. Okay. Okay, so let's take a look at Lewis dot structures. Okay, so first of all, we have a duet rule. The duet rule is a very tiny rule. It only covers hydrogen and helium. And that's because hydrogen and helium are in row 1, and row 1 only has a 1s shell. It doesn't have any p orbitals. It only has s orbitals, which means it can only take 2 electrons. It's stable with 2 electrons. So the duet rule literally means that hydrogen will always have 2 electrons on it. Okay. And you could even go farther than that by saying that hydrogen will always have 1 bond and no lone pair electrons. Okay, I don't give you always rules very often, so that is one that you probably want to write down. Okay, now let's take a look at our next one, and we have what's called the octet rule. So beginning with boron, elements are stable when surrounded by 8 electrons. This fills the s and p orbitals of their outer shell. So if we look at fluorine, remember fluorine is 1s2, 2s2, 2p6. So their outer shell, 2s2, 2p6, counts for 8 electrons. And that's when it's the most stable. Well, sorry, this would be, not fluorine, sorry, this is neon. And that's what they're going for. Fluorine, we know, is 1s2, 2s2, 2p5. And so it needs 1. And so you could say, all right, well, here's a space where it needs a pair, and here's a space where it needs a pair. So what can happen is that you'll end up with these electrons here, these 2 electrons forming a bond. So we can draw them here between them. Now, this model here shows the dots between them, but more commonly, we would draw fluorine gas like this. 1 bond means 2 electrons. And sometimes people will leave the dots in between, and I actually really don't like that. I very much prefer that the dots in between be a bond, because it's very important to identify the difference between your lone pair electrons and your bonded electrons. Okay, so let's look at drawing Lewis dot structures. And the simplest Lewis dot structure that we can build is water. And the first thing that we want to do is we want to add up all of our valence electrons. So each hydrogen gives us 1, and there's 2 of them. And there's 6 electrons for the oxygen, and that gives us 8 total. And if you're wondering what I'm doing for finding that, all I'm doing is I'm looking at my periodic table, and I start on the left side and I count the number of electrons atoms I have until I get there, ignoring, and this is important, ignoring the transition elements. So it would take me 6 to get to oxygen. If I go down to arsenic, it would take me 5 to get to arsenic and 7 to get to bromine. So that's how I'm picking those valence electrons. All right. So now use a pair of electrons to form a bond between each pair of bound atoms. Okay, so that's what I've done is I just come down here and I say HOH. Okay, good. But now that accounts for 2, 4, and we need 8. So we have 4 more. Okay, so then we have our structure with our lone pair electrons to account for everything there. All right, so now let's take a look at a couple of things here. We have single covalent bonds, and that is a bond in which two atoms share one pair of electrons. I'm going to use this opportunity to go through and work on this. Okay, so we have two hydrogens, 1 + 1. We have two valence electrons to account for. And so we place a bond between them, and that is our 2 when we are done. Now let's take a look at something new. We have a double covalent bond, and that's a bond in which two atoms share two pairs of electrons. So let's show you how this would go about. Carbon has 4, and then we have 2 oxygens, so plus 2 oxygens, 12, 16. So we have 16 valence electrons. So now watch what happens. We can place our carbon, okay, and there's multiple ways of doing this. Sometimes you'll watch videos and they'll start with the dots, and you could definitely do that. You could say, okay, well, my carbon has 4 like this. So I know that it has 4 sites for bonding, and my oxygen has 1, 2, 3, 4, 5, 6, and it has 2 sites for bonding. And then you could draw another one up here. So 1, 2, 3, 4, 5, 6. And that's one way to do it. So one way to do it is to start with it like this. And one way to do it is to start with it like I have over here. And in this case, the one that I have drawn here that I'm sort of waving my pointer around, I have 4 electrons. Okay, and I would walk through this and say, okay, so now I've used 4 and I have 12 more to place. Now, remember, we have to follow the octet rule if we're not talking about hydrogen. So these have to come together. So what we could do, well, so first we say, okay, so 2, 4, 6, 8, 10, and 12. Okay, now when I, 2, 4, 6, 8, 10, 12, 14, and 16. There we go. Now I have all of my electrons accounted for. My carbon is stable because it has 8 electrons around it, but my oxygen is not stable because it only has 6 electrons around it. So what do? I can't put any more electrons on because they don't exist. In the law of conservation of mass says, yeah, just make something up. Okay, so I need to do something. So, well, what you do is you can take these lone pairs from the carbon and you can add them in. You can keep making bonds so that you have more around it. Okay, so when I brought those in, now I have something that looks like this. And I have 2, 4, 6, 8, 10, 12, 14, 16. And this accounts for everything. So you don't usually start with that. With the structure that you have over here, people will often draw these and they'll draw bonds. So like this. See? And then once you do that, you can kind of see where everything is. And then you would rearrange it. Okay. I think both methods work really, really well. Part of the problem is that sometimes you will end up with something that doesn't follow the rules. Every now and then you will have 3 lone pairs on oxygen and only 1 bond. It's not real common, but it's not uncommon either. And you'll see me work through some of those. So be careful being stuck with this. The Lewis dot structures that the atoms themselves come with are not set in stone. All right, now let's look at nitrogen. Nitrogen, each one has 5. So we have 10 valence electrons. Okay, and again, let me show you the 2 ways of doing it. First, you could just draw like this. That's 2, and then 4, 6, 8, 10. Okay, and now I can see that each one is not quite satisfied. So what I could do is I could move in this top pair like that. Okay, and now the one on the right has 8 electrons, but the one on the left only has 6. So now I need to move in another pair, and nitrogen gas will look like this with a triple bond. Another way of doing it, if we're using this other method, okay, is to draw our 2 nitrogens like so. And notice because I have some knowledge, I'm kind of orienting them right away. And you can sort of see this. If you draw it like this, I very much do not want you to leave it like this. This is not a Lewis dot structure. I don't want to see it like this. You can start like this, but then you must rewrite it to indicate a traditional Lewis dot structure. Okay. All right, now the next thing that we're going to do is we're going to draw some Lewis dot structures. And I think actually I really want to break things up. I don't want this video to get too long. So we're going to do this slide and then we're going to take a short break and then I will finish it. Okay, so let's take a look at what these will end up being. We have hydrofluoric acid. So we always start by adding our valence electrons. 1 + 7 = 8. Okay, and then I'm going to place them like so. I know that hydrogen can only have 1 bond, so everything else has to go on fluorine. And I have 8 electrons accounted for. You know, all of these, if I, yeah, okay. Then we have phosphorus tribromide. Now for this one, what I'm actually going to do, we know that we have 5, and then we have 3 bromines. So 7, so that's 21 + 5 is 26 electrons. Now I know that bromine is a halogen, it's going to look just like fluorine, but I want to remember what phosphorus looks like. And I think that's when this gets really easy. And so I'm going to use this as my guide. And so I'm going to come over here and I'm going to place those lone pairs on the phosphorus. And I'm going to use it as my guide like so. And once I use it as my guide, then probably what I'll do before I do anything else is I'll make my bromines look like halogens as well. Don't skimp on the dots. Okay, I know they take time, but you have to include them. Okay, now what I need to do here, I can see that everything's satisfied the octet, but I need to make sure that I have 26. So I have 2, 4, that'll be confusing. Okay, I'm just counting 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Yay. Now I know that I am correct here. You don't have to count them with something that is apparent. I'm just erasing my yellows and I'll put the greens back in. Okay. All right. Now we have NH3, and I'm going to remember also that the primary Lewis structure for nitrogen looks like this. Okay. And that's going to help me with the idea. First, I must start with 5 plus 3 times 1. It gives me 8 electrons for ammonia. And so I have 2, 4, 6, 8, and I'm done. All right, now oxygen. Let's take a look at oxygen. Sometimes these diatomic molecules are funny. Okay, oxygen has 6 plus 6 or 12 electrons. Okay, and I'm going to place them sort of like this. And I would have 2, 4, 6, 8, 10, 12. Okay, so I've put everything around here, but my oxygen on the right is not satisfied. So I need to bring in another bond. And now it works out. And you'd probably see it drawn a little bit more like this. I won't, as long as I can tell that your electrons are in dots, and it's okay if they're in odd places. This will help you with the idea of where things are placed later though. All right, now we have carbon tetrachloride, and carbon tetrachloride is 4 plus 4 times 7. That gives us 28, 32 valence electrons. Okay, now with this one, I would probably start with the idea of what does carbon look like? Carbon looks like this, and it can have 4 bonds on it. So, and you almost always see carbon with its 4 bonds. And chlorine is a halogen. So let's see if this works out. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everything has 8 and I have 32, so I'm good. Our last one here, HCN. So we have 1 plus 4 plus 5. And remember, I'm adding up my valence electrons. That makes this one 10. Okay, now with this the way it is, it actually, in this case, isn't really useful to have all this here. It would be more useful to start drawing bonds. And we're going to draw it exactly as it's written. Now, I know that hydrogen is done, 1 bond, no lone pair electrons, and that's an always, always, always. Now, let's take a look here. So we've got 10 more, we've got 10 electrons, we've got 4 used. So let's say, okay, well, we've got 2, 4, 6, 8, 10. All right, great. Well, not great because the carbon only has 2 bonds on it and it needs 8 electrons. So what I'm going to do is I'm going to take some of my electrons off here and I'm going to bring those in. And now I have 8 electrons on my nitrogen, 8 on my carbon, and 2 on my hydrogen. And those are basic Lewis dot structures that follow the rules. And that's where I'm going to leave you with this video, and I'll be back in just a bit for the next one. Ooh.